a little bit of my introduction. So I have done my MTech from IIT Kharagpur. I have done MSc from Politecnico di Milano, Italy, and I was also doing some research work there. I was also doing some research work in Italy. Okay, are you able to see what I am writing on the PPT? Can you please tell me? Is my writing clear? Okay, ठीक है. I have around 5+ years of teaching experience, and my AIR score in 2015, and I have taken after that as well. So it was 675. Then I went for my MTech, and then I went out of India. Okay, so chalo ठीक है. And if you want, you can also join my Telegram channel, The Learning Curve. Okay, for agar if I'm doing outside anything, I'm taking YouTube sessions or anything, like you can get the updates there. ठीक है, चलो ये हो गया. Now, today we are going to start heat transfer. Let us take a view on the official GATE syllabus. Okay, although we are going to cover, I mean, GATE syllabus does not tell you each and every topic that we are going to cover, but it is a broad syllabus. कि भाई ठीक है, there are so many topics that come under these topics, but it is a good idea that we will take a look on what the official GATE syllabus is. Okay, chalo ठीक है. It is first is mode of heat transfer. So today we are going to cover this modes of heat transfer. How many modes of heat transfer? Can you tell me in the chat box if you have done, if you have little bit idea how many there are? How many? Yes, very nice, Sean. Yes, Shruti, very nice. There are 3 modes of heat transfer. We are going to see each and every. For today we are going to see an overview, then we will take them individually, okay, in much detail later on. Then we will go to one-dimensional heat conduction, resistance concept, and electrical analogy. This we are going to do tomorrow. Okay, then heat transfer through fins. This we are going to do in the, actually this is lecture 2 and lecture 3. This is lecture 1. Then fins will be lecture 4. Okay, unsteady state will be lecture 5, and then everything will come in unsteady state. Then this is convection. This is portion is convection. From here, let me change the color of the pen. So this is your convection from here to here. Yeah, this is your convection. We will take, I am not saying convection is not important, but for GATE it is not very important. Very few questions will be asked from convection, although it is a very wide concept. A lot of research happens on convection. Okay, and a lot of industry, like when you go to industry, so a lot of concepts are applied from here, but according to GATE it is not important. Our objective in this class is to cover what is important as per GATE. Okay, if I teach you everything, so then your focus will shift to unimportant topics. I want that your focus should be on the important topics, so that you will get a good score in GATE. Chalo. Heat exchanger, then we will move to heat exchanger. Heat exchanger we will take in lecture 6 and 7. Okay, so this is all heat exchanger. Then we will go to radiative heat transfer, Wiens. This is all radiation, and we will take this lecture 8, 9 and 10, I think. And then convection we will take in lecture 11, 12, 13. Something like this we are going to take. I am not saying it is bound that we are going to take lectures like this, but this is how I am planning. Okay, so in 12 or 13 lectures, we will finish everything that is required. I just need your commitment. Because look, I don't want to reduce the content. Whatever is important, I am going to cover. But there are times that I will not be able to cover that in 2 hours. So I want your commitment that you will be with me for whatever time it takes. Maybe 2.5 hours it can take. Okay, so I hope that you will be with me if you actually want to cover all those topics. If you are not interested, you want me कि भाई नहीं sir, you whatever you want to cover, you cover in 2 hours, then I can also do that, no problem. ठीक है, तो be with me for whatever time I am there. That is your commitment. Okay, because if you are targeting GATE 2023, so beta, this is actually the peak time. Okay, right, this time at least you would be studying around 12-13 hours, I am hoping. Okay, so this time your commitment, your motivation should be at the peak. Okay, so if I am taking 3 hours, so or 2.5 hours, I hope that you would not have any problem. Chalo. Now let us take, or tomorrow I am going to tell you already, make up your mind, tomorrow class can go long because we have to cover so many things, and we will cover in tomorrow's class. It is afternoon duration. Tomorrow class is at 1 p.m., right? 1 to 3 p.m. But I hope that we will stay together for more time. Okay, chalo. So what is the average weightage of heat and mass transfer? You see, in the last 6 years, I am telling you, from 2017 to 22, you see, in 22, of 8 marks they have asked at heat transfer of 8 marks. Although it is exception, I am not saying in 2023 it will come of 8 marks or 5 marks or 4 marks, but let us take an average. So the average is 5.2 marks. 5.2 marks for heat transfer. 5.25, that is 5 and 5 quarters, like 5, not 5.5, but 5.25 marks on an average. I have taken the average of 6 years. So I am hoping around 5 marks will come out of heat and mass transfer. Plus minus 1 or 2 marks. It can go to 6 marks. It can also go to 4 marks. ठीक है? तो इतना ठीक है तुम लोग? Is it okay for you people? Okay. Tell me one more thing, because like I come from north. ठीक है, तो I sometimes Hindi comes in my language, although I try to be almost 100%, to be in English, but maybe kabhi kabhar, like maybe once in a while I speak Hindi. So how comfortable are you with Hindi? Just tell me, like out of 10, how comfortable are you in Hindi? Are Shruti, is 10 out of 10 means you are very comfortable. Is it? Okay, Sean says 3. Okay, so 3 is not a good number. So I'll still try to be focused on English. Okay, Sean. I hope that is convenient for you. The lecture will be in English only. I am just saying sometimes I use few words that unintentionally comes out of my mouth, but that has no relevance according to the lecture. Okay, chalo. Okay. Let's move on. Now let us see which chapters are important. Which chapters? So conduction is a chapter, convection is a chapter, flow over. This is also a convection part. Okay. Then radiation is a chapter, heat exchanger, and fins and unsteady state. So if we see that conduction is the maximum questions will come from conduction and radiation. Maximum questions they have asked from conduction and radiation. Okay, convection, as I was telling you, look, out of total, which you have to study a lot for convection, there are no questions from flow over pipes and plates. And if I say even these 8 questions, no, it is not of pure convection. It is basically conduction plus convection, which we are going to cover anyway. But this core portion of convection, which takes a lot of time, a lot of hard work, but there are no questions. Very few questions are asked from this portion. Okay, but it is going to take a lot of time to understand this. But anyway, we cannot skip because it is a part, because it is given in official syllabus as well. You see, it is given in flow over flat plate and throw pipes. It is given, so we cannot skip this. Although in last 6 years, they have not asked a single question out in the last 6 years. But we cannot do anything. We have to cover this anyway. Okay, chalo. Fins and unsteady state is also 5 marks, and this is 8 marks, heat exchanger. So the main topics that you need to focus on is, first is conduction, second is radiation, and the third is heat exchanger. These are main topics that you need to cover, and you need to solve more and more questions on this. You have to very, very, very focused on these topics, and whatever confusion you have, you write to me. Okay, maybe I can also join your WhatsApp group. I think there is some WhatsApp group as well. I will join that soon. You can ask there, you can ask me personally as well, no problem. Okay, you can ask in the class as well. Chalo, अब आ जाते हैं, let's come to the main topic. So we are going to introduce heat and mass transfer. Okay, so सबसे पहले we have to understand, first of all we have to understand what is the difference between thermodynamics and heat and mass transfer. You see, in heat transfer, let's say heat and mass transfer or heat transfer. So whenever we talk about heat transfer, so we talk about this much heat is getting transferred, that much heat is getting transferred, how the heat is getting transferred. So we talk heat transfer, heat transfer, heat transfer so many times. But if you remember, if you have already done thermodynamics, you have already talked about heat transfer so many times, isn't it? In thermodynamics, we also talk about work transfer and heat transfer. So much discussion has already been done on heat transfer in thermodynamics. Then why are we studying a completely different subject, heat and mass transfer, to understand heat transfer? Okay, so the difference that we need to understand. So what is the difference? The difference is, so thermodynamics deals with the system in equilibrium. Okay, so there is first equilibrium system, there is second equilibrium system. It will only know, thermodynamic will only deal what is happening at first equilibrium system and at the second equilibrium system. What is happening in between, thermodynamics does not care. It do not know anything what is happening in between. Okay, and it tells you the amount of energy transfer, the quantity. Amount means the quantity, how much quantity of heat transfer has taken place from one equilibrium state to another equilibrium state. That is what thermodynamics tells you. But when we come to heat transfer subject, it deals with the rate of heat transfer. Rate means flow, how it is flowing. So here, heat transfer is a function of time. How the heat transfer is changing from equilibrium one state to two state. In between, what is happening, heat transfer deals with. So, and that is why it is always expressed as joule per second or watt. In heat transfer, whenever we talk about heat, we always express that this in watt. But in thermodynamics, when we talk about heat, we say joule, not joule per second. We always say joule. Okay, so let us take an example here. Okay, let us take an example. Let us take what? So there is a bucket of water. You see, we have a bucket and there is some water in this. So this water, this is water. A lot of water is there. Lot of water with infinite heat capacity. Okay, that means its temperature is not, it can absorb any amount of heat, but its temperature is not going to change. If you have studied thermodynamics, then you already know that heat reservoirs have infinite heat capacity. Whatever heat you take from thermal reservoir or whatever heat you give to thermal reservoir, their temperature do not change. So it is the same thing. Okay, and let's say its temperature is T infinity. Now let us take a very hot ball. Let us take a very hot ball. Okay, it is a steel ball or some copper ball, hot ball, and it is a temperature TH. Okay, so now when you dip this ball in this water, so this ball I have dipped, it is a TH. Okay, so at the moment, at the very moment when you have dipped this ball, time is equals to 0 seconds. Time is equals to 0 second. And what is the temperature of ball? Temperature is TH. Okay, now after some time, maybe 5 minutes, 10 minutes, 15 minutes, whatever time, after T is equals to T second, what will happen? A heat transfer will take place from the ball to the water. So ball will reject heat, water will absorb heat. Okay, and the temperature of ball will reduce. So finally, the temperature of ball will come to T infinity. So it is your first equilibrium state, and this is your second equilibrium state. Okay, this is your first equilibrium state, and the second one is your second equilibrium state. Now, when we talk about thermodynamics, so what will thermodynamics be able to calculate? Thermodynamics will be able to calculate total heat transfer quantity. How much heat is transferred, total heat transfer from equilibrium state 1 to equilibrium state 2. When this ball has come from temperature TH, initial temperature TH, to final temperature T infinity, what is the total heat is transferred from the ball to the water? Thermodynamics will tell you this. Okay, what else it will tell you? It will tell you the final temperature as well. Final temperature. What will be the final temperature attained by the ball? Okay, chalo. Final equilibrium temperature. Final equilibrium. 1 second. Equilibrium temperature. But when we talk about heat transfer, when we talk about heat transfer, yeah, HMT, yeah, heat and mass transfer. Now here heat transfer is a function of time. We are talking about how the heat transfer taking place in between these equilibrium temperature. When from equilibrium state 1 to 2, how the heat is transferred in between. So here we determine Q as a function of time. Okay, so and this is called as rate of heat transfer. Whenever heat transfer is expressed with respect to time, which is called as flow rate. Okay, this is called as rate of heat transfer. Okay, so what will HMT tell you? What will HMT tell you? Time required, how much time is required to attain, time required to attain or to reach from first equilibrium state to second equilibrium state. Okay, in thermodynamics we never talk about time. I don't know if it's going to take 1 hour or 2 hours. I don't know. Only heat transfer equations, conduction equation, convection equation, radiation equations can tell you how much time it is going to take from first equilibrium state to second equilibrium state. Also, it can tell you any intermediate temperature at any time t seconds, not the final. If let's say this final equilibrium state has reached after 10 minutes, okay, but heat transfer can tell you how much what is the temperature at t is equals to 5 seconds. It can tell you what is the temperature at 60 seconds, at 1 minute. So it can tell you when the heat transfer is taking place at any given time, what is the intermediate temperature. Okay, is it clear what is the difference between thermodynamics and heat and mass transfer? Okay, in thermodynamics we do not care about time. In thermodynamics we do not care about time. Okay, so for example, if you if you go to a coffee shop and you drink, for example, you go to a coffee shop and you order coffee. Now if you do not like the coffee, so you leave it at the counter. Okay, and eventually what will happen, that the coffee cup will lose heat until it will come to the surrounding temperature. But by using thermodynamic equations, you can calculate what is the total heat transfer, because you are not worried about how much time it is going to take to reach to any particular temperature. But for example, you want to drink that coffee, so now you are concerned ki bhai, at how much time it is going to take to reach the coffee at a particular temperature, at a particular comfortable temperature. Okay, so then you can use heat and mass transfer equations and find out ki bhai, after this time, after these many minutes, this coffee will come from 50 degrees Celsius to 30 degrees Celsius, and at 30 degrees Celsius you can drink it. Okay, so whenever you talk about time, you talk about heat and mass transfer. In thermodynamics we have never talked about time, right? Chalo. Now, so today we are going to discuss the three modes of heat transfer. First is conduction, second is convection, and third is radiation. We are going to talk about that. In today we are going to talk about them in brief, but then we are going to move on and we are going to talk about them individually in detail. Okay, chalo. Let us talk about the conduction first. Let us talk about conduction. What is conduction? By conduction is the mode of heat transfer that occurs due to temperature difference within the same body or between or from one body to another that are in physical contact, okay. So first of all, what is the requirement hai that you have a body where you have to focus here. A lot of people will tell you that conduction happens only in solid, or in the definition they will write it is a mode of heat transfer that occurs in solid due to temperature difference. Okay, so some people will add here occurs in solid. I am going to tell you this is not correct. Okay, can you tell me, have you heard this key conduction happens in solid? Can you tell me, have you heard this? So it is not necessary that conduction happens in solid. Okay, it is not necessary. It can happen in solid, liquid, and gases. Chalo. So look, this is a single body. This is a single body, and at this side we have temperature T1, and the other side we have temperature T2. Okay, and in order for the conduction to happen, there must be a temperature difference. That means T1 cannot be equal to T2. There will be a higher temperature, there will be a lower temperature. So let us assume that T1 is greater than T2. Okay, so according to second law of thermodynamics, heat transfer will happen from high to low temperature. So heat transfer will happen from high to low temperature. So it will happen in this direction, Q, because this is high temperature, this is low temperature. Okay, so see, is it satisfying all the equations? Look, first of all, we have a temperature difference. Yes. Now within the same body, yes, it is happening within the same body. If you maintain the two sides at different temperatures, then one side will get cooler and the other side will get hotter depending on the temperature difference. Okay, and other body we will see in some time, and if they are in physical contact. So what do you mean physical contact? Now let us take one more body. For example, you have two bodies here. Okay, and this is temperature T3, and here we can say T3 is less than T2. So now this heat transfer will take place and it will go like this. Okay, now there must be a physical contact between these bodies for conduction to happen. Okay, so all the three conditions must be satisfied. First, what? Temperature difference must be there. Then either same body or two bodies. So there must be a body, there must be some matter, there must be a medium. Okay, without medium it cannot happen, and there must be a physical contact. So these three conditions must satisfy. Okay, so conduction can take place in solid, liquids, and gases. It can happen in, should the phase of body in contact should be same? No, it's not necessary. It's not a necessary condition. Okay, we are going to see when we go to convection, we are going to see that in convection. Okay, we will come to that, don't worry about that. Okay, but convection is basically, okay, let us, when I'll come to that today only. Okay, do not worry, I'll answer your question as well there. Okay, I'll chalo. So it will happen in solid, liquids, and gases. So see, let's see how it happens. So first of all, solids. How the conduction happens in solid. So in conduction, what happens? Solid, what do the solid body have? Let's say we have a solid body. So it will have some molecules. Okay, and these molecules are attached with each other. Okay, like this. And then there are some free electrons as well. Free electrons. There are some free electrons here, 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 here. So whenever, let's say you apply some heat transfer here, for example, like you put a hot body or some fire you put here, so you are giving heat transfer from here. Now what will happen? So first of all, these electrons, you see this side will be at higher temperature, this side will be at lower temperature because you are giving heat from one side. Okay, so what will happen? These electrons, their energy will increase, and they will jump from one side to the other, and it will transfer energy. in terms of heat to the another electron. So heat transfer will transfer from this side to this side. Okay, this will jump, this will transfer heat to this. Okay, so this is called as free electron energy transfer. Now, what is the other phenomena? The other phenomena is molecular lattice vibration energy transfer. Okay, now when you transfer heat, there are some molecules that is nearby to this heat transfer. Okay, this side. So these molecules will vibrate around their mean position. They will vibrate. And when they will vibrate, let me draw it with a different color. Okay, they will vibrate around their mean position. And for example, this is vibrating here. So it will transfer heat to this one. Now this will vibrate, this will transfer heat to this one. Then this will vibrate, this will transfer heat to this one. So because of molecular lattice vibration energy, because of molecules vibration, one energy transfer takes place, and because of free electrons, energy transfer takes place in solid. It is very important. I am talking about solid here, not any other medium, not liquid, not gases, only solid. There are two phenomena. First is molecular lattice vibration energy transfer, free electron energy transfer. Okay, now you need to understand that in metals, there are large number of free electrons, and therefore free electron transfer dominate. Most of the heat transfer in metals happens because of moving of the electron from one place to another. Okay, moving of the electron from one place to another. But in non-metals, very little or no free electron, and therefore molecular lattice vibrational energy transfer phenomena dominates. Is it clear? Shruti, tell me, is it clear? Okay, chalo. Let us move on to liquids then. Now, what happens in liquid? So, in liquids, let's say we have some water here. Liquid means it can be water, it can be oil, anything. Okay. Now, of course, even if it is water, it will have some molecules, right? It will have some molecules. But one second. But these molecules are farther apart. In solids, they are closer. But in liquids, they are farther apart than solids. In liquids, the molecules are farther apart than solids. Okay. Now, what will happen? Let's say I'll transfer heat. I'll set up a fire here and I'll transfer heat from here. So the molecules, now when you go this side, temperature is reducing. Here we have T infinity. T infinity is environmental temperature. Here we have some higher temperature. T higher is greater than T infinity. Okay. So the molecules that are closer to the lower bottom, what will happen? They will gain energy. And they will move. And they will collide with the other molecule. It will collide here. It can also go here. This can also go here. This can also go here. Okay. So first of all, it is colliding with the other molecule. The molecules that are closer to the higher temperature layer, it is getting energy. It is going to higher energy state and it is moving and it is colliding with other molecules. Okay. So this is the first phenomena. Now what happens in liquids? We have intermolecular forces, right? Intermolecular forces. Now, because of these intermolecular forces, these molecules, when they come, for example, if this molecule will, just 1 second, for example, it is jumping from here to here. Now it is going to get attached, it is going to remain in contact with the other molecule for some time. Because of what? Because of intermolecular forces. Okay, so first of all, collision is happening because of the heat transfer, and then because of intermolecular forces, they are combined with each other. They will stay in physical contact with each other for some time. They will stay in physical contact with each other in some time. Now this is at higher temperature, this one is at lower temperature, so heat transfer will happen, and this is called as diffusion of heat. Diffusion means heat is getting diffused. Heat is diffused from molecule at higher temperature TH to lower temperature, to from molecule at higher temperature to molecule at lower temperature. Okay, so now in the liquids there are two phenomena. What? Collision of molecules and diffusion of heat. Because of this, heat transfer takes place. Is it clear? Tell me very quickly, is it clear? Okay, chalo. Let's talk about gases. Now we all know, if we have gases, for example, we have this and we have gas here, for example, air. So one molecule will be here, one will be here, one will be here, one will be here. No intermolecular forces, no intermolecular forces between, intermolecular forces between what? Molecules only. The force between molecule is intermolecular forces. Okay, now there are no intermolecular forces. So what will happen, for example, if you give heat here, fire, if you put fire and give heat, then this molecule is going to take heat, come to a higher energy state and collide with the other molecule. Now the chances of colliding is very less. So chances, therefore, and that is the reason that the heat transfer in gases is very, very low as well by conduction. Okay, so the only phenomena that causes heat transfer is collision of molecules. You have to identify what we are talking about. We are talking about gases. Okay, we started with solids. Then we talked about in liquids, and now we are talking about gases. So in gases, the only phenomena that causes conduction heat transfer is collision of molecules. Collision of molecules. Because the molecules are very far away, therefore we know that the chances of collision are very low, and therefore heat transfer due to conduction is low. Okay? Or also you have to understand that according to kinetic theory of gases, we get this equation. This is called a Boltzmann equation. Okay, now here velocity of molecule is, this k is Boltzmann constant, this k is BOAL. Boltzmann constant, and this is molar mass. Okay, so velocity is proportional to temperature. This is temperature T. This is temperature. Okay, so velocity is proportional to this. Now the heat transfer is happening. The heat transfer is happening because of velocity only. So velocity is also proportional to heat transfer, and also we will see thermal conductivity very soon. Okay, so therefore I can also write that K is directly proportional to T. Okay, this is thermal conductivity. We are going to see in much detail thermal conductivity. Okay, so this equation is important. This equation is important. They both equations are important. Okay, ठीक है, gases समझ में आया? Is are this phenomena in gases are clear? Is clear? चलो चलो ठीक है. Now, So now we are going to see the governing equation for conduction. Okay, conduction happens, but what is the equation that governs the conduction heat transfer? Now that is the Fourier's law of conduction. That is called the Fourier's law of conduction. Now before we move to Fourier's law of conduction, okay, there are certain assumptions that we need to see. Okay, and these assumptions we are going to slowly remove, and we are going to talk about each and every phenomenon later on. But you have to see that the first assumption is steady state heat conduction. What does it mean? Steady state means the property is not changing with time. Property is not changing with time. Okay, for example, there is a body here and heat transfer is happening like this. So this is the direction of x. Now at time t is equals to 0, at time t is equals to 1 second, at time t is equals to 5 seconds, the same amount of heat transfer will happen. And because same amount of heat transfer is happening, the temperature T1 this side and T2 this side will remain same. Temperature is not changing with time. Temperature on either side will remain T1 and T2 only. Because for any application, for example, if you want to, if you want to run a turbine, so you want steam at a particular temperature. Okay, so now whatever you need to do, you do, but the temperature will remain same for all practical applications. For example, if I want to maintain a certain temperature in this room, so whatever heat I need to remove from this room, from this wall or from anything, but I still need to want to maintain the constant temperature. Okay, so constant temperature must be maintained at any time. For that, the same amount of heat will be transferred. It will not matter that after at t is equals to 0, the temperature was 25 degrees Celsius, and at t is equals to 5 seconds, the temperature here is, let's say, 35. That means it is not steady state. It is unsteady state. Okay, so we are assuming it is steady state. Temperature will remain same. It is not changing with time. Temperature is not changing with time. ठीक है, then unidirectional. अब देखो, just 1 second. Okay, unidirectional. Unidirectional means the temperature is varying in only one direction. For example, this is x direction, this is y direction, and this is z direction. Okay, this is a solid body like this. This is the z direction. Now, if y and z direction are very big compared to the x direction, for example, what? Your window, you see, if you see your window, your glass window, then only the horizontal direction heat transfer takes place. If you see your height and if you see this direction, your height and width, this is very small. These are very large. These are very large. Okay, if this is your window, this is your window, so these dimensions are very large. Y and z, only this direction, x direction, only heat transfer takes place. So that is the case of one dimensional heat conduction. Only temperature is changing in only x direction, only in one direction. It can change in y and z direction, yes, but the change in temperature is very insignificant. This very little change in there in y and z direction, so we can neglect them. Okay, then we have, there is no heat generation inside the body. Inside the body there is no heat generation source. Now what is the example where heat generation can take place? For example, nuclear rod. Okay, where heat generation take place is nuclear rod, which we are going to address separately when we will come to that. Okay, then these are some very basic assumptions, that material is homogeneous and isotropic, and temperature gradient is constant. Temperature gradient is constant. Okay, chalo. Now let us come to the main part. Fourier's law of conduction. Fourier's law of conduction. Okay, chalo, theek hai. Let's draw a diagram first. Let us take a body. Okay, let us take a body. Now we are assuming that we want to maintain T1 here and T2 here, and T1 is less than, T1 is greater than T2, because we are transferring heat from this side. Okay, so that how will, if this is your temperature and this is your x direction, so as x is increasing, temperature is decreasing. Okay, as x is increasing, temperature is decreasing, temperature is decreasing, and this is the body. Okay, now let's see what does a Fourier law says. Now Fourier law says that the rate of heat transfer along a given direction, what is the direction? X direction. We are only talking about x direction. Okay, so rate of heat transfer, whenever you write rate of heat transfer, you write dot here. Okay, so in x direction, due to conduction, okay, it is directly proportional to the area of heat transfer perpendicular to the direction of heat transfer. Perpendicular area, what is the perpendicular area? You see the heat transfer is taking place in this direction, so what is the perpendicular area? This is the perpendicular area. Let's say this is your L, this is your, let's say, width, and this is your height. So what is the area? Area is equals to width into height. Yes, y into z. Yes. Then it also says that it is proportional to temperature gradient along that direction. Temperature gradient dt by dx. dt by dx. Now what is dt by dx? By at any point, this is your dt, change in temperature, and this is your dx, change in small dx with a dt. This is called as temperature gradient. Now we all know, as x is increasing, as we are going in this direction, temperature is decreasing. Okay, so what can I write? T2 minus T1 upon x2 minus x1. We know that T2 is less than T1 and x2 is greater than x1. So this will be a negative quantity. This will be a negative quantity. Okay, because this will come as negative. T2 is smaller than T1. Okay, चलो ठीक है. तो हम क्या can we write it by combining these two? Can we write that heat transfer due to conduction in x direction is proportional to perpendicular area and temperature gradient? Yes, we can write this. Okay, chalo. So from here, let me write it here. Qx conduction is proportional to perpendicular area into dt by dx. Okay, now if I remove a proportionality sign, I'll add a proportionality constant k, and I'll write like this. Okay, now k here is thermal conductivity, and it is a property of the material. So each material, metal, non-metal, liquid, water, gases, everyone have their own thermal conductivity. Okay, now what is the unit? So thermal conductivity unit has watt per meter Kelvin. Okay, so let us check what is the units we are getting. Conductivity as watt per meter Kelvin. Area we have meter, and dt is in Kelvin. This is temperature, and this is meter. So meter, this will cancel, k will cancel, and this heat transfer you will get in watts, which is also called as joules per second. Joule per second. Now, as I have told you one thing, what I have told you, this term is negative. This term is negative because you see, as x is increasing, t is decreasing. So this term will come negative. Now, in order to get a positive heat transfer, because this will come as negative, we know it will come as negative. So what we do? We add a minus sign here. Now, why are we adding this minus sign? To satisfy second law of thermodynamics. Why? Heat transfer will happen from high temperature to low temperature. So whenever someone asks you why this negative sign, say, sir, it is to satisfy second law of thermodynamics, because the temperature gradient is negative. As x is increasing, temperature is decreasing. And to get a positive value, we add a minus sign here. ठीक है? Is it clear? Is it clear? चलो ठीक है, बढ़ते हैं आगे. लेट्स गो अहेड. कॉन्सेप्ट ऑफ थर्मल कंडक्टिविटी. तो थर्मल कंडक्टिविटी क्या है? You see, we have defined Fourier law. Fourier's law as Qx conduction is equals to minus Ka dt by dx. Okay. Now, if I want to define K, so K is equals to Qx conduction dx area into dt. You have to know what is it. Okay, dx is this, it is x1, it is x2, so thickness, it is thickness. Okay, chalo. Now how conductivity, so this is the defining equation, it is the defining equation for thermal conductivity. Defining equation for thermal conductivity. How do you define? The amount of heat transfer, the rate of heat transfer, it is rate of heat transfer through a unit thickness, means dx is equals to 1 of a material per unit area, means area is equals to 1 meter square. Okay, and per unit temperature difference delta T is equals to 1 degree Celsius. So if I put this here, Qx conduction, always know that there is a dot here. Okay, 1 upon 1 into 1, so K is equals to thermal conductivity. Okay, so that means if more heat transfer is happening, more heat transfer, that means rate of heat transfer is high. Okay, let me write it in a different way. If I say rate of heat transfer is high, means heat is getting transferred from one side to the other side very fast, very fastly. That means thermal conductivity is high. Okay, so if a thermal conductivity is high, the rate of heat transfer will be high, or you can say it vice versa. If the rate of heat transfer is high, that means that material has high thermal conductivity. Okay, so it basically tells us the ability of the material to conduct heat, and its unit is watt per meter Kelvin, and it is the property of material. Okay, clear हुआ इतना? Is it clear? चलो. So let us see the thermal conductivity of certain materials. For example, in metals, at room temperature we are talking about, because thermal conductivity is a function of temperature as well. We are going to see in some time. Okay, but we are saying we are talking about room temperature, at room temperature. Okay, so we see in metals we have high thermal conductivity in the range of hundreds. Silver has 410, copper has 385, aluminum 200, pure iron 80, steel is 15 to 35. In non-metals, it is in the range of 10:1. You see, 1.2 glass wool. But there is a point here. In diamond, it is a non-metal, but it has very high thermal conductivity. Very high thermal conductivity. It is an exception. We are going to talk about this in a little while. Okay, only diamond is exception. Otherwise I will conclude this in some time. But let us say in liquids. So in liquids also, it in the range of 10 to the power 1, say 10 to the power minus 1. And in gases, it is very low. Okay, so I can conclude here that thermal conductivity in metals is the highest, and then in non-metals, then in liquids, and then in gases. But there is an exception here. Diamond is a exception. Why diamond is exception? Why diamond is exception? So let's see. See what happens in a diamond. You see, diamond has a very perfect crystalline structure. You see, molecules. Although it is non-metal, so very little amount of electrons are there. Very little or no electrons are there. But it has a perfectly crystalline structure. Now we all know that in solids, heat transfer takes place because of molecular lattice vibration and free electron transfer. Now, because of free electrons in diamond, there is negligible heat transfer. There is no heat transfer, negligible. But the heat transfer due to, because the molecules are so perfectly arranged, they are so perfectly arranged that they can transfer heat very quickly. Okay, so because of this, heat transfer is very high, and because of this, the conductivity of diamond is very high. Okay, so what is the reason that thermal conductivity of diamond is very high, or diamond is a perfect thermal conductor? Because of its perfectly crystalline structure. In diamond, all the four valence electrons are covalently bonded and no free electrons. And electrical conductivity is because of free electrons. So diamond is a electrical insulator. It is an electrical insulator because it has no free electrons, but is a perfect thermal conductor. Okay, is it clear? चलो ठीक है, आगे बढ़ते हैं. So ये क्वेश्चन देख लो. This is GATE 2001 1 mark question in a decreasing order. Decreasing order we have to find out the thermal conductivity. First is pure iron, then liquid water, then saturated water vapor, and pure aluminium. So how can we arrange this? Can you tell me what is the right answer? B, A, B, C. Yes, that is correct. Shruti, yes. Sean, yes, that is correct. Right. Okay. This has 80 and this has 20 watt per meter Kelvin. Watt per meter Kelvin. Okay. And we all already know that liquid water will have the second, second lowest, and thus water vapor will have the lowest thermal conductivity. So DABC is the right answer. Chaliye. Now, how the thermal conductivity varies with temperature? How the thermal conductivity varies with temperature? Okay, chalo dekhte hain. Let's see. So as I have told you that in solids, heat transfer. We are talking about solids. Then we will talk about liquids and gases. Okay. So what will happen now? Let's say you have a solid body and it has some thermal conductivity K. But when you start giving heat, then its temperature is going to increase. So how the thermal conductivity is going to be affected by the increase in temperature? Okay, so what do we know? That in solids, heat transfer takes place because of molecular lattice vibration and free electron transfer. So what will happen? Look, we have, and then we have free electrons. Okay, we have free electrons as well. Now, when you increase the temperature, what will happen? First of all, we know that in solids, this is the phenomena that dominates mostly. Okay. Now, when you increase the temperature, the vibration of the molecules is so random. The randomness of molecular vibrations increases. Okay. The randomness, the molecules start vibrating at a very random order. They are not even colliding, they are not even transferring it, they're just vibrating at a very random way, in a very random way. Okay. And because of the random vibration, what will happen? They restrict the flow of free electrons. They restrict the flow of free electrons. The molecules are vibrating so vigorously, so randomly, that they are not even allowing the electrons to flow from one place to the other. So it will restrict the heat transfer because of this. It will reduce the heat transfer because of this. And it is already low. This is already low. The total heat transfer is going to reduce in the solids if you are increasing the temperature. Okay, the rate of heat transfer, very important. The rate of heat transfer is going to reduce. And I can say, because we have already know that K is equal to Q dot conduction. And therefore, I can say that thermal conductivity for solids also reduces with temperature. So as temperature increases, thermal conductivity of solid decreases. इतना समझ में आया? Is it clear? चलिए, let's talk about liquids. So what did we talk about in liquids? Now liquids heat transfer takes place because of collisions of molecule and diffusion of heat. Now what will happen? You are giving heat. Because of this, the temperature is going to increase. Okay. If the temperature is increasing, molecule will have more energy. They will absorb more energy. Yes, of course. Okay. And they will collide more frequently, more frequent collision or faster collisions. Let me write faster collisions. Okay. Yeah, more number of collisions. So faster collisions, they will collide with each other very frequently because now they have higher energy state. So they are colliding like anything with each other. Okay, faster collisions. That means more number of collisions. But what is happening? Because their intermolecular forces will decrease, because now they have more energy, they can break the bond between each other. So their intermolecular forces has come down. And earlier, when one molecule, like these are two molecules, so it will coming here and it was staying here, and then the diffusion was happening. But now it is not staying here. Now it has very high energy. It will collide and it will move ahead. Okay, so intermolecular forces will decrease and molecules will not diffuse heat. Okay, so number of collisions is increasing, but because diffusion of heat is not happening, so as you increase the temperature, rate of heat transfer is decreasing, and conductivity is also decreasing. Okay, this heat, how you are increasing the temperature? By providing some heat. Okay, some heat source with a fire or something. But now the rate of heat transfer is going to decrease, and thermal conductivity is also going to decrease. So higher the temperature, lower the thermal conductivity, except in the case of water. In liquids, okay, here increase in temperature decreases the thermal conductivity except aluminium and uranium. Okay, is it clear? Shruti, is it clear? Okay, one more person has joined. Shridev, how are you? Yes, I can go back. Sure. This one. ठीक है, is it clear? चलो अब हम आते हैं गैसेस पे. So what happens in gases? We all know that you are increasing temperature and heat transfer happens because of collisions of molecule. Okay, as you increase the temperature, energy level of molecules will increase. That means number of collisions will increase, and that means heat transfer will increase, and that means thermal conductivity of gases will increase. So I can conclude that as temperature of gases increases, thermal conductivity of gases increases. Okay, on increasing the temperature of gases, their thermal conductivity also increases. At high temperature molecules move faster and there will be more number of collisions per unit time. Okay, तो अगर आपको conclude करना है, if I need to conclude, so I can say what can I say, that in solids as temperature increases, thermal conductivity decreases. In liquids, as temperature increases, thermal conductivity decreases. In gases, as temperature increases, thermal conductivity increases. That is the brief. Is it clear? Is it clear? Okay, very nice. So you can also see in this graph, you can also see this is from Yunus Sengel. This is Sengel book, Yunus A. Sengel, I think. Okay. Now you can see here, look, if I talk about gases, so this is thermal conductivity. Okay. Temperature, I'm sorry, this is temperature in Kelvin and this is thermal conductivity. Okay. So as you are increasing the temperature, the thermal conductivity of gases, air, helium, steam, argon is increasing. It is going up, right? It is going up. But in solids, silver, copper, gold, it is coming down. It is coming down. So it is decreasing. In solids, K is decreasing as you are increasing the temperature. Also, you can see in carbon tetrachloride, these are liquids, and even in water. So water, it is first increasing and then decreasing. Okay, so I have given you exception of aluminium, that in aluminium sometimes thermal conductivity increases with decrease in temperature, with increase in temperature, sorry. Okay, but here it shows a horizontal line. But in some books, sometimes they show that aluminium thermal conductivity increases when temperature increases. Okay, so it's okay. But in general, I can say that if, as I have briefed you, that this is the general conclusion. This is the most accepted conclusion. Okay, chalo, ये question देख लो. As the temperature gate 2014 1 mark question, very simple question. 1 mark in your hand. What is the right answer? Yes, very nice. A is the right answer. Okay. Just now we have understood that in gases, as temperature increases, thermal conductivity of gas increases. Okay, very nice. चलिए आगे बढ़ते हैं. अब आ जाते हैं हम next mode of convection, next mode of heat transfer, which is convection. Okay, so Now, what does the definition of convection say? It is the mode of heat transfer that occurs between a solid body and a surrounding fluid. Now, it is also not a generalized definition. I don't know, but people use this equation very frequently. Like sometimes there is not a solid body, but there can be a convection. I will give you an example as well. Okay, so there can be. Okay, I'll give you some example in some time. Okay, chalo. Now it says it is a mode of heat transfer that generally occurs between a solid body and a surrounding fluid due to temperature difference associated with macroscopic bulk motion of the fluid transporting thermal energy. Don't worry. I don't know if you understood this equation, this definition. Let us understand piece by piece. Okay. It is a mode of heat transfer that occurs between a solid body. So we need a solid body first of all. Let's say this is the solid body. Okay. We have a solid body. Okay, and we need a surrounding fluid, so there must be a surrounding fluid. Okay, let's say air, water, whatever you want to call it. Okay, and there is a surrounding fluid. Now due to temperature difference, matlab there must be a temperature difference. If this surrounding fluid is at T infinity and this surface is at Ts, then Ts is not equal to T infinity. Either it is higher or lower. Okay, so temperature difference will also be there, and the macroscopic bulk motion of the fluid transporting thermal energy. That means that there must be a fluid velocity, fluid must be moving. If the fluid will not be moving, then convection will not happen. Then what will happen? Conduction will happen. Okay, if only, what do you have? You have a solid body and a fluid over it. The fluid is not moving. The fluid is not moving. Then what will happen? Only conduction will happen. Okay, we will see that. We will also see that. You see, now this fluid is coming here. The fluid is coming here. And let's say I am assuming that T surface is at a greater temperature than T infinity. So this is at lower temperature. Okay. Now this fluid is coming. It is taking heat. It is coming in contact with the surface. It is taking heat and moving away. Then other fluid is coming. It is taking heat and moving away. So fluid must have a velocity. Fluid must have a velocity. There must be a fluid motion. Macroscopic bulk motion of the fluid must be there. So there must be three conditions that must satisfy so that you can say that the convection is happening. What? First of all, it only occurs at the interface. It will only occur at the surface, at the interface. Okay. Then temperature difference must be there. Temperature difference must be there. Temperature difference must be there. And fluid motion must be there. Three conditions must satisfy. And I have shown you how these three conditions looks like. Okay. Only it will happen at the surface only. This surface only it will happen. It will not go inside the solid. Only at the interface on surface it will happen. And there must be a temperature difference between the solid body and the fluid. And the fluid must be moving. These three conditions must satisfy. Then only you can say that convection is happening. Is it clear? Is it clear? चलो ठीक है. Now conduction and convection अब हम देख लेते हैं. चलो conduction जो है, when we talk about conduction, let us talk about conduction. So conduction, we said that it happens internally. It is an internal phenomena. It is an internal. It happens inside the body. It is an internal phenomenon. And it needs physical contact. Physical contact. But convection happens at the surface. So it is a surface phenomena or a interface phenomena or a boundary phenomena, whatever you want to call it. Boundary phenomena. Okay. Now this boundary could be a solid and fluid boundary, like we have just seen, or it could be a fluid boundary. Fluid boundary, for example, what? We have water here. This is water. And air is flowing over it. So heat transfer that will take place at the interface will be convection heat transfer. Okay, so it could be fluid. Now, I hope you already know then when we say fluid, it means it could mean anything, liquid or gas. Okay, ठीक है? So convection is a surface phenomena. It happens at the interface. It happens at the interface. Okay. Also you must know this, that you see at the surface here, at the surface, when this fluid is coming here and at the surface of the solid body, the fluid velocity will be zero. Fluid velocity will be zero. Okay, because of no slip condition that I think you have read in fluid mechanics. No, yes, no slip condition. And then as you are going up, you are going up, so there are separate fluid layers. Okay, there are separate fluid layers. Now these fluid layers are transferring heat. These fluid layers are transferring heat from this layer to this layer to this layer. Then this will transfer to this. So as you are going up, the fluid motion is increasing. The fluid motion is increasing. Okay, so at the surface, what is happening? At the surface, what is happening? Conduction is happening, because I have told you that for convection, there must be a fluid motion. But at the surface, because of no slip condition, fluid velocity is zero. So at the surface, between solid and fluid, what is happening? Conduction is happening. Conduction is happening. So, Sean, is that clear? You were asking key if solid is not there, or I don't know what was your question. So different phases you were saying. Okay, so different phase we have, but conduction is happening. Okay, and when you go up, so when fluid transfer is happening, so that is happening advection. Combining both, what is called? It is called convection. It is called convection. Okay, so at the surface, at the interface, because there is no fluid velocity, it is called as conduction. And as you go up, fluid layer transfer heat from one layer to another, it is called as advection. So conduction plus advection is called as convection. Is it clear? Is it clear to everyone? चलिए आगे बढ़ते हैं. Let's go ahead. Okay, now free and forced convection. Now I have told you that for a convection to happen, one necessary condition is fluid motion. Fluid must have some velocity. Okay, now based on the forces causing fluid motion, what are the forces that are causing the fluid motion? I can classify convection into two types. What are the types? Free convection and forced convection. What do you mean by free convection? Means no external force is causing the fluid motion. Then what is causing? Buoyancy forces. Because of buoyancy forces, the fluid is moving. Okay, due to density change. Here, external forces are used. External forces are used to cause fluid motion. What kind of external forces? So you can apply a pump, you can apply a fan, you can apply a blower. Okay, is it clear? Tell me very quickly, is it clear? Example for free convection, all the natural phenomena that is happening. You see, air is flowing over your body, and it is taking away heat, right? So what is that? Are you applying any external force for it? No, it is just when it is coming in, because your body is hot. Okay, after a run, your body is hot. So the cold air is coming, it is taking heat from your body and moving ahead. So that is free convection. All natural phenomena are free convection. ठीक है? चलिए, let us move ahead. Is it clear? चलो. So if you want to see, for example, I'll tell you example. Let's say you have a solid plate and you have a ball here. Okay, hot ball. This is at TH, hot ball, and air is coming. Air is coming at T infinity. Okay. Now what will happen? It will come in contact with this ball, and because TH is greater than T infinity. Okay. So this air will take heat. Okay. Heat transfer will happen, and the molecules, the density of air will decrease. And when the density will decrease, it is going to move up. And then the next layer will come. It will also take heat. It will also move up because density is decreasing. So it will move up. So this is free convection. But in forced convection, for the same, for example, you want to cool this ball at a faster rate. You want to cool it more quickly. Okay. So what do? Now, let's say this is your air. Okay. Now you apply a fan here. And you're rotating this fan. So what will happen? Air will come, take heat and move ahead. Air will come, take heat and move ahead. Here also it will come and move ahead. It will take heat and move ahead. Okay. So, but it has a faster heat transfer rate. Okay. It has a slower heat transfer rate. Heat is removed very slowly in free convection. In forced convection, quickly, very faster rate heat transfer takes place by convection. ठीक है? Is it clear? चलिए. अच्छा, there are 3 people: Sean, Shridev, Shruti. Tell me very quickly, how much rank are you targeting in GATE 2023? What are your expectations from yourself? What do you think? How much you want to, or you think you can score in GATE 2023? Just your self evaluation. At what stage of preparation are you? Under 100, under 500, under 1000, whatever what you are expecting, whatever you want to. I mean, it's just a general discussion. You can get much better than that, of course, but I am just asking. चलिए. Currently 40 to 45. What does this mean, 40 to 45? I don't understand. Percentile? No, not percentile, Sean. 40 to 45 percentile is very low. You means number of marks are you thinking that you can get 40 to 45 marks out of 100? Acha. Okay, 40 to 45 questions out of 65. Okay. What about Shruti and Shridev? How much are you thinking that you have covered this much syllabus? You are comfortable in that? You are able to solve questions, previous GATE questions? Out of 100, you tell me how much marks are you targeting? You write it down and let me start. Between 40 to 60. Okay, Shruti, 40 to 60 is a very wide range. Okay, above 60. Okay, very nice. 40 to 60 is a very wide range. Okay, narrow it down to 5 marks. Let's say focus on 55 to 60. So you need to come on that. Okay, or 60 to 65. Otherwise, that means there is so much variations in your preparation. You are not very comfortable in some. I mean, I am just making assumptions based on what you have told me. So if you have covered certain syllabus, maybe focus more on the syllabus that you have covered, because you have to narrow it down. So that you will have some confidence. I have covered 5 subjects, so whatever will come, I'll 99% I'll get correct answers. I will attempt all the questions. So maybe practice more questions. ठीक है, get precise preparation so that you narrow it down to, ठीक है, I'll get 55 to 60 or 50 to 55, like this. कि भाई if the question come from this subject, I will solve it whatever happens, no problem. ठीक है, चलिए आगे बढ़ते हैं, let's move ahead. चलो, now the governing law for convection. Governing law for convection, what is the governing law? भाई governing law for conduction क्या है? Tell me, what is the governing law for conduction? What is the governing law for conduction? बताओ यार, टेल मी वेरी क्विकली, हाउ मच टाइम आर यू टेकिंग? गवर्निंग लॉ फॉर कंडक्शन, 4 years लॉ यार, वी जस्ट टॉक्ड अबाउट दैट, है ना? इट्स 4 years लॉ ऑफ कंडक्शन, isn't it? So why so much confusion? Just now we have finished that. I'm just waiting for you to was thinking about the syllabus and other subject. Okay, don't think too much. Okay, chalo. Shruti, what happened? You don't know what is the governing law of conduction? We have just covered, no? Yes, 4 years law. So why didn't you write? Right? No, always suddenly went blank. Okay. चलिए कोई नहीं, it's okay. ठीक है. But that is the reason that you revise it. You revise before our next class. Otherwise, everything will go mess up in your mind, and you need to sort out each and everything on the same day, so that whenever anything related to this comes in the next lecture, you will have your second revision, third revision, fourth revision. But if you are already confused with the topics that we have covered, then that confusion will only increase. It will not, because okay, chalo, and revise. Please revise before tomorrow's class. चलिए ठीक है. Then only you will be able to enjoy the lecture. Otherwise, after 2-3 lectures, when everything will mess up in your mind, no, you will lose motivation in this. Okay, that is a truth. So please revise before tomorrow's class. Then only you will be able to enjoy tomorrow's class. ठीक है. चलिए, let's move ahead. We have less time and we have a lot of content to cover. चलिए. Now Newton's law of cooling. It is the governing law for convection. It says that the rate of heat transfer by convection is directly proportional to. So rate of heat transfer by convection is directly proportional to temperature difference between the body and its surrounding. So what is this? Ts minus T infinity. We know what is Ts. Where is this? This is Ts, surface body temperature, and this is T infinity. Okay, and it is also proportional to area of heat transfer. Q dot convection is proportional to area of heat transfer. What area? Area that is exposed to fluid. For example, which area? You see this area. This area. This is exposed to the fluid. This area. This is the area for whatever area that is exposed to the fluid is the area of heat transfer. Okay, so this is the area. Okay, so if I combine both of them, can I write Q dot convection is proportional to area of heat transfer, Ts minus T infinity. And if I remove this sign, let me introduce another variable, Ts minus T infinity. Okay, now what is H? H is heat transfer coefficient. Heat transfer coefficient. Very, very important characteristic of this heat transfer coefficient is that it is not a property. It is not a property of material. Thermal conductivity, we have seen it is the property of material, but heat transfer coefficient H is not a property of material. It is not a property of material. Okay, then Then let us first of all, and its unit is watt per meter square Kelvin. Okay, so let us see the unit of this. H is in watt per meter square Kelvin. Area is in meter square, and this is Kelvin. So Kelvin, Kelvin, this. So the unit is watt. Okay, now, so heat transfer coefficient. H is heat transfer coefficient. And it is very important, and it is not a property of material. It is not a property of material. Okay, now then, how do you determine this? It depends on the flow parameters, how the flow is happening, how the flow of fluid is happening, free convection, forced convection, what is the velocity. Okay, so depends on the flow conditions and fluid properties. Okay, so I can say that H is a function of so many variables: velocity of the fluid, characteristic dimension. Okay, if you have a solid body like this, if you have a rectangular body like this, if you have a circular body like this, if you have a sphere like sphere ball, so what is the orientation? So characteristic dimension. Okay, what is the density of the fluid, viscosity of the fluid, specific heat of fluid, thermal conductivity of fluid. It depends on so many parameters. Okay, so we have to experimentally define this. Experimentally defined the value of this. Okay, is it clear? चलिए, तो next is, now experimentally we have defined certain heat transfer coefficient for certain conditions. Okay, watt per meter square Kelvin. Tell me very quickly, what is the unit of thermal conductivity? Without delaying, very quickly tell me in the comment box, what is the unit of thermal conductivity? Watt per meter Kelvin. Yes, that is correct. Very nice. That is correct. Okay. So here we have meter square, watt per meter square Kelvin. Okay, very important. A lot of people get confused in the units of thermal conductivity and heat transfer coefficient, but you should not have any confusion. The thermal conductivity unit is watt per meter Kelvin, and heat transfer coefficient is watt per meter square Kelvin. Okay, now you see here, and you also need to know that heat transfer coefficient in free convection is always less than heat transfer coefficient in forced convection. Okay, so you see here we have, what do we have? Free convection and forced convection in gases. So gases are same, but free and forced convection. So of course, free convection will have lower H and forced convection will have higher H. Okay, similarly you can see in water, free and forced convection. So in free convection it is lower, in forced convection it is higher. But you see here, if you compare, you can also compare with gases and liquid. So gases, H of liquids is greater than H of gases. So this is one conclusion, this is another conclusion. This is for gases and this is for liquids. Also, condensation heat transfer, when you are condensing something, condensation means what? When vapor is converted to liquid, you are removing heat. So it is in the range of 3000 to 25,000. And then last is boiling. Boiling is what? When you are converting liquid to vapor or gas, liquid to vapor or gas. It is the highest heat transfer coefficient. Okay, so these are few things that you need to, I don't know, remember, because there are no logic behind it, but we already know that in free convection, look, this is one conclusion that you understand. This is another conclusion that you must understand, and then you know you also have to remember this. Okay, so I can say that heat transfer coefficient in boiling is greater than heat transfer coefficient in condensation. Is heat transfer in liquids, in liquid forced, heat transfer in liquid free, heat transfer in gas is forced, convection, and is greater than heat transfer in gases free. Is it clear? These are some general conclusions that we have defined. Is it clear? Chaliye. Let's move ahead. Very nice. Now let us come to the last mode of heat transfer, which is radiation. Okay. Let us come to the last mode of heat transfer, which is radiation. So what about radiation? Let us consider a room. You have a room, right? And you have suspended, you have, hanged a hot body in that room. Okay. And you have removed, you have suspended the hot body and you have removed all the air from the room. So now there is no medium, no air inside the room. And so this is at ball temperature, and out the walls is at room temperature, or let's say T infinity. Okay. And we know that ball temperature is greater than T infinity. Now, let us see one thing. First point. Look, the ball and the room wall is at T infinity. Wall is at T infinity and ball temperature is TB. Wall and wall are two confusing words. Let me say boundary. Okay, let me say room boundary. So room boundary is at T infinity and ball inside ball is at TB. And there is no physical contact. So no physical contact. So if there is no physical contact, so can I say there is no conduction heat transfer? Right? I can say that there is no conduction that is happening here. There is no conduction that is happening. Now, up there is no fluid. There is no surrounding fluid. No surrounding fluid. There is no fluid that is moving. Okay. So can I say there is no convection as well? There is no convection as well. But you see, but still, after some time, with time, the ball will cool down. It will cool down. It will lose heat. Okay. It will cool down to room temperature, room wall temperature. Eventually, after 1 hour, after 2 hours, after one day. I'm not saying after what time, but after some time, the ball will also come to the room temperature T infinity. Right? And after this, thermal equilibrium will be achieved. Now the ball and room are at the same temperature. Thermal equilibrium is achieved. So now you see here, there is no conduction, there is no convection. Then what? How the heat is losing? Now here the phenomena that is responsible for this heat transfer is radiation. That means radiation do not need a physical contact. No physical contact. And no material medium. It does not require any material medium. Is it clear? Tell me very quickly, is it clear? Okay, very nice, very nice. So can I say that conduction, convection, they require material medium for heat transfer, but radiation does not require any material medium for heat transfer. and it is the fastest mode of heat transfer. And for all or most of the practical applications, even your body at room temperature, you see, at room temperature, conduction heat transfer, convection heat transfer, and radiation heat transfer, all three heat transfer takes place simultaneously. What is conduction heat transfer? You see, you eat something, and due to your metabolic activity, your body, your inside of your body gets hot. Okay, and that heat is getting transferred to the outside surface of your body. Now the air is flowing outside your body surface, right, outside your body skin, and it is taking away heat, so convection is happening. And with conduction and convection, we do not know, but radiation is also happening. My body is radiating heat continuously. Okay, so all the heat transfer happens simultaneously for all practical applications. ठीक है, चलिए. Now, so radiation is the propagation of emission of heat in the form of electromagnetic waves. So this does not require a material medium. It happens in the form of electromagnetic waves. Now, why? How the electromagnetic waves are emitted? Electromagnetic waves are emitted as a result of vibration motions of the atom and rotational motion. Okay, we all know that any body that have molecules, that have, you know, atoms and molecules are continuously vibrating, they are rotating about each other, they are having translation motion. Okay, so basically they are all moving inside our body, however insignificant that motion is, but they are moving, right? And this vibrational and rotational motion stops only at 0 Kelvin, which is not achievable. You cannot achieve 0 Kelvin. You see, third law of thermodynamics, not achievable. What is third law of thermodynamics? Third law of thermodynamics says that at 0 Kelvin you can achieve, the entropy will be zero, and it is the most stable state. Okay, so at 0 Kelvin, all the vibration motion, rotation motion, translation motion of atoms is zero. But you cannot achieve 0 Kelvin. That means all bodies at temperature higher than 0 Kelvin, which we know that all the bodies are at higher temperature, whatever the temperature it is, room temperature, any temperature, whatever it is. So all the bodies which are at higher temperature than 0 Kelvin, they radiate heat because they have vibrational motion, rotational motion. So because of that, they can emit electromagnetic waves, and because they can emit electromagnetic waves, they are emitting radiations. Okay, now there is a whole wavelength based on frequency and wavelength. There is a whole electromagnetic spectrum. This whole thing is called as electromagnetic spectrum. So many rays are there, but because we are only focused on heat transfer, which is due to temperature difference, we are only focused on temperature heat transfer that is happening because of temperature difference. So it comes under the category of thermal radiation. So thermal radiation has 0.1 to 200 range. This range is thermal radiation. Okay, and out of this, what do we have? We have some infrared radiations, we have some visible light, and we have some ultraviolet rays. Okay, चलिए. So thermal radiation के बारे में what do we know? It is the electromagnetic radiation emitted by the body due to temperature difference. No, it is not because of temperature difference. It is because of the temperature. Conduction, convection requires a temperature difference, but it does not require temperature difference. It requires that a temperature must be at a temperature above than 0 Kelvin. So all bodies at all temperature emits thermal radiation. That means if we have two bodies, body A, body B. Now let's say this is at T1 temperature, this is at T2 temperature. Okay, and let me assume T1 is higher than T2. So now because it is at T1, which is higher than 0 Kelvin, so it will radiate some heat. Okay, let's radiate some emission radiations. Okay, so it is radiating. Now body B is absorbing those radiations, yes, but because it is at higher temperature than higher than 1 second, because it is at higher temperature than T2 is greater than 0 Kelvin, T1 is also greater than 0 Kelvin. Okay, now because it is at higher temperature than 0 Kelvin and but it is lower than T1. Okay, so it is going to absorb as well, it is going to radiate as well, it is going to radiate as well. Any body at any temperature except at 0 Kelvin will radiate heat, it will release heat. Okay, now the amount of radiation depends on the temperature. For example, T1 is higher, so it is radiating more heat, E1, let's say R1, R2, R3, radiation 1, radiation 2, radiation 3. But because body 2 is at lower temperature than T1, so it is radiating less radiations. Okay, less radiations are coming out, less emissions are happening. So higher the temperature, higher the radiation heat transfer. But any body at any temperature higher than 0 Kelvin will radiate heat. Okay, so body A will radiate more heat than it will receive. So if I need to calculate a net radiation heat transfer, net, are you able to understand what I am saying? Net radiation heat transfer from body A. I am just talking about body A, not about body B, just talking about body A. Okay, so body A, how can I calculate? Body A for heat received by body A minus heat rejected. Okay, so I can say Q of heat transfer of body A by radiation is equals to Q in minus Q out. Lost radiation, yes, you can also say that. You can also say that heat rejected. Yeah, actually it should be like this only. Heat rejected upon heat received. But anyway, it does not, just 1 second, heat received. But anyway, if you are getting negative, what does it mean? If you are getting negative, this value negative, if you are getting, what do you mean by that? 1 second, let me just Q out minus Q in. It simply means that it is if lost radiation minus, yeah, that is true. But if it comes negative, yani in minus out, if it comes negative, that means in is less than out. Okay, yes, we are gaining heat. In is no. If I say that Q in minus Q out is negative, that means Q in is less than Q out. That means you are receiving less heat. Yes, in is less. The body will cool down. But in this case, you are gaining heat. If it comes positive, that means you are gaining heat. You are gaining, right? If it comes positive, means Q out is greater than, no, it is also losing heat. It is also losing heat. Okay. If it comes positive, because we are talking about radiation heat, right? How much is going out? So if it comes positive, means again we are losing heat. Again we are losing heat. You see, no? If it is positive, means Q out will be greater than Q in. Means Q out is more, Q in will be less. That means you are giving more heat, so body will cool down. Okay? Is it clear? We don't have to rely on any single formula. Okay, just you should know the concept. That's it. That is more than enough. चलिए, और वैसे it is asking net radiation heat transfer. So how much heat is transferring? So that is why it is Q out minus Q in. Okay, it is transferring this much amount of heat. Chaliye, let's move on. So before we come to the last concept of governing law of radiation, we must understand black body. What is black body? We all know, we all have heard about black body. Okay, so a black body is defined as a perfect emitter and a perfect absorber. It emits all the radiations that are incident on it, and it has also the capability of absorbing all the radiations. Okay, now a black body absorbs all incident radiation regardless of wavelength and direction. It does not matter what is the wavelength, what is the direction. Okay, it can absorb all heat at a specified temperature and wavelength. At a particular wavelength and temperature, no surface can emit more energy than a black body. Okay, and black body emits radiation energy uniformly in all direction per unit area normal to the direction of surface. So if this is the surface, if this is the surface, so the radiations are uniformly distributed in all directions. Okay, so radiations or emissive power is not a function of direction. It is uniformly distributed in all directions, and that kind of radiation are called as diffused radiations. Diffused, it is called as diffused radiations. Okay, now this is not diffused. Okay, you see here the radiations are more, but here in this direction radiations are not more, so it is not diffused. These are real body radiation. It is also written, it is a real body radiation. Okay, is it clear? Shruti, why are you not answering now? Tell me very quickly, is there any confusion, anything, whatever it is? Black body can emit and absorb too, yes. Okay, so it actually, the point is that it depends on what kind of body you are using. Okay, so for example, like if there is a surface, if there is a surface, so whatever is coming here, it can actually radiate everything whatever is coming. But there could be a, for example, if a white body, this is a black body. Okay, a white color body, this is for example ice or snow. Okay, so whatever radiations are coming over it, it can absorb. So it does not matter how it looks, but it can show, it can show both the phenomena. For example, you see, if there is a body like this, if there is a body like this, and there is a small hole here, there is a small hole. Look, do not confuse that there is a body that is black. Okay, or there is actual nahi. First of all, do not confuse that a body that looks black in color is a black body. Secondly, do not confuse that black body is a real concept. Okay, any body that can even absorb 99% of the emissions, you can say okay, it is close to black body, but there is no black body. For example, there is a very big body and there is a small hole, very small hole here. Okay, and now some radiation are coming here and it is entering here. Now once it is entered, now it will go here. Okay, it is reflecting also. You see, it is reflecting whatever is coming. Now it will reflect here, and it is reflecting here, it is reflecting here, it is reflecting here, it is reflecting here, but it is not going out. It is inside the body, it has absorbed everything, and it is reflecting also. Okay, so it is the characteristic that we have assumed, because we are assuming it is a perfect body. I am not saying there is a body that can do this both at the same time, but it is the characteristics that are assumed to be ideal, that if there is a perfect body it can show these characteristics. Okay, now you see here, whatever is entering here is absorbed Okay, and it is reflected also, so it can be called as a black body. ठीक है? Is it clear? चलिए, now let us come to the last concept of today. So today you people are lucky because I am leaving you at time, but tomorrow this will not be the case. So prepare yourself mentally because I am going to take more time tomorrow. Okay, because tomorrow a lot of concept we need to cover and a very important, because from tomorrow's session at least one question you will get in gate exam. I am very sure, and you see that you it will happen. Okay, chalo. Stephen Boltzmann's look at what does Stephen Boltzmann's law says. It says the radiation energy emitted from the surface of a black body, that means radiation energy emitted from a black body per unit area per unit time is directly proportional to the fourth power of its absolute temperature. If there is a body, its temperature is T. Okay. So if it is a black body, so it can emit, one second, it can emit radiations which is directly proportional to fourth power of its absolute temperature. Very important point here is that this T you must keep in Kelvin. You must keep in Kelvin. Never put this in degree Celsius. Never and never put this in degree Celsius. Whatever you do, never put this in degree Celsius. Okay. So this is in Kelvin. Now, if I remove the proportionality sign, it is sigma T to the power 4, and sigma is Stephen Boltzmann's constant, which is the value of 5.67 into 10 to the power minus 8 watt per meter square, Kelvin 4. Okay, and the unit here is watt per meter square. That's what it is saying. You see, per unit area. So this is per unit area and per unit time. So this is what? Joule per second meter square. So it is per unit time, it is per unit area, and this is fourth power of its absolute temperature. Okay, is it clear? What area? We have not talked about area here. When we talk about area later on, so what will be the area? Look, if this is the body, this is, we will talk about this later only, but for example, this is the body and it is radiating heat from here, emission radiation. So what area will be there? Tell me. This area. Okay, chalo. Now let us conclude, one second. So what have we understood today? We started with difference between thermodynamics and heat transfer. I hope that was clear. Then our main focus was on modes of heat transfer. We talked about conduction. Conduction में we talked about definition. Okay. Then we talked about mechanism or conduction mechanism in solids, liquids, and gases. Now I am not writing everything because I have already told. So in solids, what do we have? Molecular lattice vibration energy and free electron transfer. In liquid, we have collisions and diffusion. In this, we have only collisions. Okay. Then we talked about what? Uh, Governing law, Fourier's law of conduction. Okay. Qx of conduction is equals to minus K A dt by dx. Okay. Here we talked about thermal conductivity concept, thermal conductivity. Okay. Unit is what? Watt per meter Kelvin. Okay. And then we have talked about variation of thermal conductivity with temperature in solids, liquids, and gases. So we all know as temperature increases, thermal conductivity decreases. Here, as temperature increases, thermal conductivity decreases. Here, as temperature increases, thermal conductivity increases. Okay, then we have talked about convection. Okay, so we have talked about definition. We have talked about free and forced convection, and we have talked about governing law, which is Newton's law of cooling. क्या होता है? Q convection is equals to heat transfer coefficient HA Ts minus T infinity. Okay, and then we have talked about radiation phenomena, definition, and we have also talked about black body a little bit, which we are going to later on talk about again when we come to radiation. And we have talked about Stephen Boltzmann's law. Stephen Boltzmann law. What is this? EB is equals to sigma T to the power 4 watt per meter square. What is this unit? Watt. What is this unit? Watt. Yes, heat transfer coefficient we have also talked about. Very nice. We have talked about heat transfer coefficient. Do you have any confusion in heat transfer coefficient, Sean? Okay, very nice. Then these are the topics. Maybe one or two topics that I forgot. Right now I did not write, but whatever we have covered enough today. Okay. Now, is it up? Tell me how much are you happy with today's lecture? I mean, what were you expecting? What were you expecting from today's lecture? Are you happy with today's lecture? If I want you to rate out of 10, how much do you think? Very happy, very nice. So, very nice, Sean. Thank you so much. So, I just wanted to now I did your comments as well. Okay, I mean, was my speed faster? Was my explanation more or less? Do you want me to do anything else? Like just a random, I'm asking, what do you think? Was my speed okay for you? My explanation was clear. Is it okay? Everything was okay? Okay, Sean, thank you so much. Everything is good. Okay, very nice. Chalo, let's conclude this lecture, and I am going to tell you that tomorrow we are going to talk about the heat transfer, single and composite, single and composite heat transfer. Very, very, very important heat transfer topic. And I can assure you that at least one question you are going to get in. Can we solve? Yes, we can. Of course. Look, today's lecture was very basic. Tomorrow you will say, sir, please don't solve so many questions. Yes, slides will be available. I hope that it will be available. I think I'm not very sure about the interface, but I think it will be available. Okay, if not, I can send you separately if you want. Okay. So Shruti, of course, we are going to solve more questions. Today was a basic introduction lecture, right? So anyway, whatever I got, I included some three, four questions from Gate, but we will solve the number of questions that you will say, sir, please don't solve so many questions. Okay, don't worry about that, because I know the importance of questions. I know the importance. Concepts are important, yes, but for Gate, problems are the most critical part of the preparation. Okay, and I will solve so many questions, but I still want you to practice more and more questions, not just previous year Gate questions, but book questions and other questions as well from any workbook. Okay, get any workbook in the market, practice workbook that you can get, and solve more and more questions. And you ask me that, sir, how can we solve this question? We are not able to solve this question. Whatever you want to ask, you can ask. Okay, चलिए ठीक है. So again, I am going to remind you for tomorrow's class. Tomorrow's class is at 1 p.m. to 3 p.m. But I am very sure I am not going to leave you at 3 p.m. Okay. So whatever preparations you want to do, you do it before. Tomorrow's class will be lengthy. maybe 3:30, maybe I don't know. I'm just saying it will be lengthy. So make up your mind and come to the class, and please, you will be motivated to sit in the class for 2.5 hours only when you will revise today's lecture. Then you will enjoy the tomorrow's lecture. If you don't revise today's lecture, then you will not enjoy tomorrow's lecture. So please revise today's lecture, get a little more confident on today's content, and then tomorrow we will extend the same thing. Tomorrow we are going to discuss again Fourier's law and Newton's law of cooling. We will extend the same concept. But if you remain confused in today's lecture, then we will not enjoy tomorrow's lecture. Okay. So please revise today's lecture and meet me tomorrow at 1 p.m. Okay, and I'll see you there. Thank you very much. Chaliye. Tata bye bye. I'll see you tomorrow.